Alright, so we're gonna talk about binary search tree. We call BST here. So first you need to know what is BST, right? What is a tree? A tree is pretty much just a classic data structure, right? With many used in many application. A BST provides a binary search tree that can be implemented using a linked structure. We talk about linked, right? Linked list. So this is a BST, pretty much a tree that has two children. Always two. That's why it's binary, right? A tree can have more than two, but since it's binary, so that's why it's only two. Right, and then the children also have another two, right? And it keep going like a tree, right? So the one at the top we call root, right? And we have left subtree and the right subtree. Okay, so these are example of binary tree, right? So each node in the binary tree has two subtrees or one subtree, or other children has zero subtree, right? So now let's looking at level. This is called level 0, level 1, and level 2. Okay, so we have length, depth, level, sibling, leaf, and height, right? Those are the keywords. The length of a path is the number of the edges in the path. So edges is, this is edges, node is a circle, edges, right? These are the edges. And the depth of a node is the length of the path from the root, right, to the node, right? So if you look at, this is 60 and 45, like 2 as a depth, right? 60 and 55, 1 is a depth, right? The set of all nodes at given depth is sometimes called a level of the tree. Right, level 0, 1, and 2. Siblings are nodes that share the same parent node. The root of a left, right subtree of a node is called a left-right. But a root of a left, let's say the root of a left subtree should be this, right? Of a node is called a left child of the node. That's right. And this is the right child of the node, right? A node without children is called a leaf. This is a leaf, right? At level 2. The height of a tree that contains a single node is 0. A height like this guy, height is 0, right? Because it's only itself, right? A single node. So if we don't have tree, the height is going to be -1. Is it empty? The length of the path from 60 to 45 is called 2, right? That's the length. The depth of node 60 is 0 because it's at the 0 root, right? The depth of 55 is 1. The depth of 45 is 2. Now this tree height is going to be 2, right? So 45, 57 are siblings of what? Yeah, are sibling of 55, right? And these are in the same level, 45, 57, 67, 107. And this is called a binary search tree. So if you now there's a property for BST. You see that left subtree always going to be smaller than the root, and the right subtree is always going to be greater than the root. Now, can it contain duplicate? It depends on if you want your data structure to contain duplicates. If it's duplicates, it's going to go to where? Okay, you guys tell me. Okay, if it's 60, where would another 60 go? To the right? No. It has to be on the left. It's going to be less than or equals. So where would it go? It's going to go to the left, and where in the left? Like now, if I insert 60, it has to be less than or equals, go down here. It has to be greater than 55, because remember, the right always greater than the root. So 60 is going to go down here. And it's going to be greater than 57. It's going to go down here. Create a new node and add right there. So
Search for 60 though, you only find the first 60, right?
no, I said insert.
Insert.
Insert duplicate. He talked about duplicate, right? If I insert another 60, where would it go?
But once you search for it, how do you search for the second 60? Because it'll find the first.
Okay, now we understand insert 60 for the duplicate, right? So now if you find contains, so normally it depends on your logic again. Are you search for the first one, or you keep searching for the next one? Sorry. Yes. Yeah, Lynn, can we talk in an hour? Because I cannot talk right now. Yeah, thanks. Bye. Sorry guys. Alright, let me turn this off. Alright, come back. So now you were talking about something?
Yeah. So what's duplicates? No, we're gonna find the first 60, not the next 60, right?
Yeah, we talk about now if we want to search for 60, right? It should return the first one we found, the location of the 60. Hmm?
Take less time for it to find the first one.
Where would it go next? It's know that it's going to go to the left if you want to find the second 60.
Because it's less than.
It's not going to go to the right anymore. It's going to find it right way. Make sense? Because it's know that it's greater than 55, greater than 50, than 60 right there.
There's no problem.
Alright. Any other questions?
You said on the right side it can only be greater or equal.
Yeah, that's a property. You see, greater, right always greater than the root. Left always less than or equals to the root. That makes sense?
So, binary search has only one purpose, to make searching more free.
Lock in. But
Yeah.
is it always lock in? So let's look at animations.
Straight down.
Let's look at, I'm going to go to this, right, to get animation. Link est.html. Alright, so we got add. So let's say we add, what do we want to add? 5. Alright, tell me the next number.
6.
Where would it go?
To right.
Yep. Let's try smaller. 4. Where would it go? See? Now if I get, okay, tell me what number you want to see. Yeah, yeah, yeah. Where? Where would it go? 3 less than 5?
I'll go to the -1, the right of -1.
But it had to go to the right because it's bigger than -1. Now, we understand why it's logged in, correct? Because, for example, it's going to be logged in if we have a balanced tree. Balanced tree is what? Left pretty much equivalent to right subtree, right? The wedging, right? Remember the picture of the balanced tree, right? Like this is the balanced tree, right? Let me actually get the actual picture. Balanced tree. Yeah, this is the balanced, right? Now if you look at this one, this is also a tree. Your linked list can be a tree, right? Because it's always greater to the right. So that means it's still not log n, it's going to be n. Because linked list is n. But this is going to be log n because it's going to cut off by half. I'm not going to go to right, to search for less than 4. Make sense? So that's why it's log n.
But it should be sorted into list, right? It should be sorted into list. To be primary search tree.
Then the concept is how you going to make it balanced. Right? How you going to make it balanced. Like if you insert, wonder if I can just reset, maybe refresh. So if I insert a sorted list like 1, 2, it's going to make it screwed to the right, right? So if the list is already sorted, I try to insert to it, it will not give you the best efficiency. It's going to create that linked list. Now if I try to find 5, it's going to be n, right? It's going to be here, 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 and here.
So in order to make it balanced, we should have the children on the same level.
In order to make balance, you should insert the middle first. Always go to the middle of the list for the sorted list. If you insert 3, 3 is going to be the root, right? And then, right? That's one way, right, to make always. Or another way, we have what we call AVL tree. I think they have that image too. So this is next chapter, right? So
What does AVL stand for? I think it's two people's names or something like that.
yes, the one who invented. So it's in chapter 26. Okay, I can show you a little bit. Here, this is the name of the person who inventing it. Here, Alderson, Welsky, and E.M. Landis. So A is Alderson's, Wells V, right? Welsky, and L is Landis. So that's how we're standing for, right? The Russian scientists.
So AVL, it's like another name of balance tree.
AVL tree is a balanced binary search tree.
So but
Like BST itself, it could be screwed, right, to the left, like we see, or the right. Then it's not going to be balanced. So the most efficiency is it has to be balanced. Then we guarantee that it's locked in. Correct?
I have a question. So can we go back to what's called the animation?
Which this one?
If you add -1 here,
Then it's go to the left.
balance.
It's go to the left, right? It's gonna go here, right?
So you have to have 4 more to the left to make it balance.
Right, because the balance tree is the shape of the balance tree is. Let me just show you from the slide. Is it chapter 6? Alright, so this is pretty much a slide that you want to study for your final exam too, right? So let's look at the shape of a balance tree. So this is called a complete tree. Gonna be this shape, right? This is called a full tree, right? So that means each node has 2 children, right? A complete is like the last to the left node can have 1 child, right? So this is called a full and complete, right? These are neither full nor complete, right? Because it has to go to the left before right, right? So this is complete, right? This is full and complete. This is neither full nor complete because missing the right subtree, right? This is called complete. Okay. So now your goal is to make sure that it's going to be complete or full to make it balance. Pretty much on these 2 shapes. Make sense? Because when it's in these 2 shapes, you technically gonna get about log n for sure, right? That's the goal. Make sense? Like we were talking about, one way if you try to insert the sorted list into the BST, you technically want to go in the middle and insert the middle. Always go in the middle of each. Then you always get the balanced tree, correct? Now, we also have, that's why we have another chapter talk about ABL tree, right? And ABL tree is all about, let's read the definition one more time. A balanced BST. Okay, let's say if I insert sorted order 1, now if I insert 2, if I insert 3, it's rotate. Look, it's going to rotate, push 1 down, put 2 up, and 3 to the right. If I insert 4, it's going to rotate again.
So it changed. So you balance it yourself.
Yeah, the algorithm that it implement is make it, whenever it insert, it check and it rotates, right? So if I insert 4, how would you rotate this? Okay, so let's look at ABL tree. Insert, right?
Love you too, Dad.
Let's see how they insert and rotation.
Hello friends, my name is Tushar and today I'm going to talk about AVL tree. Before talking about
think it's
AVL
gonna
tree,
be
let's talk
confusing.
about binary search tree.
This
All
is
right,
an
let
explanation
me
of AVL trees. AVL trees
put the volume
are binary search trees where we control the depth
Wow,
of the
200.
tree so it doesn't get too big.
Hello.
Maybe
Today we're
this
going
is
to
it.
discuss how insertions and rotations work in AVL trees. I'm sure you're all familiar with binary search trees.
So when you insert, you
I'm
have to
going
rotate.
discuss what
Okay.
they are very briefly. Binary tree consists of a finite set
No. Oh, I see why.
or consists of a root with left and right subtrees. Insertion is very simple and relies on the value of nodes that you want to insert and the number of nodes that are already inside the tree. Let's demonstrate it. Shown is a root with a value of 20. Let's insert a node with a value of 30. First, I will check if the value is greater than or less than the root. Since 30 is greater than 20, I will insert it in the right subtree. Now let's add a node with a value of 10. Let's check the root. Is 10 greater than or less than 20? Since it is less than, I'll insert it on the left subtree. Now let's see how to insert nodes into a BST that contains multiple nodes. Let's use the same example. Now I want to insert a node with a value of 25. First, check the root. Is the input less than or greater than the root? Since 25 is greater than 20, move down the right subtree. Next, check the root of the right subtree. Is the input less than or greater than? Since 25 is less than 30, 25 will be placed on the left subtree of the node. Now let's try to insert a node with a value of 15. Again, check the root. Since 15 is less than 20, move down the left subtree. Check again the node. Since 15 is greater than 10, move down the right subtree. Now that we know how insertion works, let's move on to AVL trees. AVL trees are self-balancing binary search trees. To see if a binary search tree is balanced, we have to check the balance factor. The balance factor for each node depends on the height of its left and right subtrees. As seen in the equation, the balance factor is equal to the height of the left subtree minus the height of the right subtree. If the balance factor is equal to -1, 0, or +1, then it is considered balanced. But if it is less than -1 or greater than +1, then the node is considered unbalanced. Now let's try to get the balance factor of each node in this BST. Let's check the balance factor of A. Since the height of its left subtree is only equal to 1, put down 1. Now let's get the height of the right subtree. Since its height is equal to 2, we subtract 2 from 1 to get -1. Now we label node A with having a balance factor of -1. Now let's check B. Since B has no children, we can say that its balance factor is equal to 0. Let's check the balance factor of C. Let's go to its left subtree. Since its left subtree only has a height of 1, we put down 1. Now, we check its right subtree. Since its right subtree has a value of 1. Now let's check D and E. Since D has no child and E has no child, we can say that they both have balance factors of 0. Now let's try to insert this node. Let's check the balance factor again. Since the height of the right subtree of node A was increased by 1, we can say that A has a balance factor now of -2. This means that node A is now unbalanced. And to balance the node, we perform what we call rotation. There are two basic kinds of rotation, left and right rotation. Let's look at left rotation first. In left rotation, from its name, we rotate left. In this example, we bring down 2 and we bring up 3. The letters pertain to subtrees with equal heights. Notice how C breaks off from 3 and attaches to 2. Let's move on to right rotation. In this figure, again, we want to break down 2 and bring up 3, just like in left rotation. Again, you can see how C breaks off from 3 and attaches to 2. Now, we're going to see when to use what kind of rotation. First, we check the balance factor. If the balance factor of a node is positive 2, this means that the left subtree is greater than the right subtree. For this, check the balance factor of the left child. If the balance factor is equal to positive 1, perform a right rotation. But if the balance factor of the child is equal to negative 1, perform a left-right rotation. A left-right rotation, from its name, is a left rotation followed by a right rotation. As you can see, after a left rotation, the balance factors become positive 2 and positive 1. Now, perform right rotation to balance out the tree again. Now, if the balance factor is equal to now, we're going to see when to use what kind of rotation. First, we check the balance factor. If the balance factor of a node is positive 2, this means that the left subtree is greater than the right subtree. For this, check the balance factor of the left child. If the balance factor is equal to positive 1, perform a right rotation. For this, check the balance factor of the left child. If the balance factor is equal to positive 1, perform a right rotation. But if the balance factor of the child is equal to negative 1, perform a left-right rotation. A left-right rotation from its name is a left rotation followed by a right rotation. As you can see, after a left rotation, the balance factors become positive 2 and positive 1. Now, perform right rotation to balance out the tree again. Now, if the balance factor of a node is negative 2, that means that the right subtree is greater than the left subtree. Now check the balance factor of the right child. If the balance factor is equal to negative 1, perform a left rotation. But if the balance factor of a child is equal to positive 1, perform a right-left rotation. Again, a right-left rotation is a right rotation followed by a left rotation. Let's look at this example. Given the following nodes, perform insertion and rotation and balance the tree. First, we insert tree and check its balance factor. Since it has no child, its balance factor is equal to 0. Next, insert 4. Since 4 is greater than 3, we put it on the right subtree. Again, let's check the balance factor of each node. Since the height of the right subtree of node 3 is greater than its left subtree, its balance factor is equal to negative 1, and 4's balance factor is just equal to 0. Now insert 8. Since 8 is greater than 3, move down the right subtree. Since 8 is greater than 4, move down again the right subtree. Again, check the balance factor. Balance factor of 8 is 0, 4, negative 1, but this time the balance factor of 3 is negative 2, indicating that it is unbalanced. Since the balance factor of 3 is negative 2 and the balance factor of 4 is negative 1, we perform right rotation. Again, we check the balance factors. Now all the balance factors are equal to 0, indicating that it is balanced. Now we insert 6. Since 6 is greater than 4 but less than 8, we put it on the left subtree of node 8. Again, we check the balance factors, but this time everything is still balanced. So we move on to the next node. We insert 7 by putting it on the right subtree of node 6. Let's check the balance factors. 4 has a balance factor of -2, 8 has a balance factor of +2, 6 has a balance factor of -1, and 7 has a factor of 0. As you can see, both 4 and 8 are in balance. But since 8 has a higher level than 4, we will balance 8 first. As you can see, 8 has a balance factor of +2, while 6 has a balance factor of -1. So we use left-right rotation. After checking the balance factor, the tree is now balanced. After inserting 5, the balance factor of 4 becomes -2, and the balance factor of 7 is +1, so we use right-left rotation. Just like from our example, notice how 5 breaks off from 6 and attaches to 4. And again, the tree is now balanced. Yay! 1. So we use the balance factor. Balance factor of 8 is 0, 4, -1. But this time, the balance factor of 3 is -2, indicating that it is unbalanced. Since the balance factor of 3 is -2 and the balance factor of 4 is -1, we perform right rotation. Again, we check the balance factors. Now all the balance factors are equal to 0, indicating that it is balanced. Now we insert 6. Since 6 is greater than 4 but less than 8, we put it on the left subtree of node 8. Again, we check the balance factors, but this time everything is still balanced. So we move on to the next node. We insert 7 by putting it on the right subtree of node 6. Let's check the balance factors. 4 has a balance factor of -2, 8 has a balance factor of +2, 6 has a balance factor of -1, and 7 has a factor of 0. As you can see, both 4 and 8 are in balance. But since 8 has a higher level than 4, we will balance 8 first. As you can see, 8 has a balance factor of +2, while 6 has a balance factor of -1. So we use left-right rotation. After checking the balance factor, the tree is now balanced. After inserting 5, the balance factor of 4 becomes -2, and the balance factor of 7 is +1, so we use right-left rotation. Just like from our example,
the balance factor of a node is the height of its right subtree minus the height of its left subtree. Okay. And we know it's balanced when minus 1, 0, or 1, which is the same thing, right? Consider left heavy when it's minus 1 and right heavy when it's plus 1. Okay, let's just use the textbook, right? So now let's start that together with example node A. So what should be a balance factor of node A? They said right minus left. Right is going to be 0, right? So, okay, if it counts T3, it's going to be 1, okay? 1 minus what?
No, 1 minus 3 because it's h plus 1.
H plus 1, right? So 1 minus 3, that's why it's minus 2, right? Okay. So A has a balance factor of minus 2, and the left shall be with a balance factor of minus 1, because 1, this guy is 1, right? Minus 2, correct? Or 0. So 0 means if it doesn't have anything. So that's why I said it could have nothing, right? So this type of imbalance can be fixed by performing a single right rotation. So our rotation pretty much just you rotate to the right. So you just make it BA. So now when you pull that up, technically A will drop down, and you see that this has 3 branches, right? You take T2 becomes part of A. Make sense? You see that? Because we know that this is going to be, like I just said, when you equal, less than equals, it's always going to be on the left of the A. So that's why. That makes sense? Alright, so now we understand this. Can we try that one more time? So
Should we start over with our own numbers?
yeah, let's start from the beginning. Okay. Let's start from the beginning. Okay. Let's start from. Let's reset our ABL tree, and then we're going to use the list. This list, right? So we start with 3, right? That should be simple. Now 4. Okay. Now 8, right? Alright, so 8 is going to go all the way to the right. So let's draw that on the board together. And check the balance factor, right? So 3, 4, 8. So this is going to be, if you use textbook, right, minus left,
Right minus left plus 2.
right? Plus 1 and 0.
0, yeah.
So what type of rotation?
It's
Left rotation.
left rotation, so we have to single rotate it right to the left.
Now the definition on this guy said
RR.
on the textbook RR, right? Plus 2 we do RR, right? So we're gonna apply RR. R mean 4, 3, and 8, correct? Correct? An example of RR again.
Does RR mean rotate to the left there?
Yes.
Yeah.
So it means
LL mean to the right, RR mean to the left.
R and then one R more. So you have first R is 4, second R is 8.
Okay.
So that's why you have to rotate to the left.
Okay.
I mean I think it's how it is. I think it's how it is.
Okay.
Yeah, like this is an example of RR, right? So you have plus 2, exactly like plus 2 plus 1, 0. You see that? Plus 2 plus 1, right? So you have to do RR, like you pull B. Let's see if B has T2. Then all things that belongs to T2 has to go and shift to A1, to A. Make sense? Okay? Because that makes sense because all the left has to be greater than A, right? Well, in this case, it's easy because 4 doesn't have. So example, if 4 happen to have something like this. Example, right? So it should look like what? 4, 3, and X, right? And then 8. That makes sense? And then we check. This is 0, this is plus 1, this is plus 1, right? So this is balanced. Correct?
So your x goes to this 3.
Yeah, because it's going to be, think about what's going to be lower than 4, 3.5, right? Then 3.5 should go, make sense?
If it's less than 3, go 2 left.
Yeah, because if it was a 3, x going to be this left.
Let's say x is 2.
Oh,
It'd be hard to get 2 there, though.
yeah. Because it's going to always go
Oh, yeah,
there,
yeah.
right? Right?
You rotate,
If we never get there, right?
Yeah, you rotate.
But something between, I mean,
Okay,
right?
yeah. Right.
All right, so but in this case, it's simplified, okay? Now we understand R. And that is pretty much the same concept, right? All right, so come back to animation. We got insert. There you go. That's how it rotates. That makes sense? All right, next we're gonna do 6, right? So where would 6 go?
See the left of 8.
So let's check.
4 is plus 1.
1 plus 1.
This is the right minus left.
So right is
2.
2 minus 1 plus 1, right?
And 8 is minus 1.
Minus 1, right? Then it's okay, right? That's why we have plus 1 minus 1 0 is okay. Alright, so let's insert the 6. Okay. Now next one, 7. Where will you go?
To the left of 6.
To
That's
the
right,
right of
six.
6, right?
Yeah.
Alright, let's check.
So it's 2 plus 3 minus 1.
3 minus 1, that's a problem now, right? Plus 2, right? 0. How about this guy?
Minus 1. It's 0 minus 1.
Left minus 1
It's
minus 2, right?
Oh yeah, that's the same.
Minus 2, right?
We can get all the number. Is that the height?
Yeah. Alright, so how would we rotate, right?
Yes.
Alright, come back to alright, so we said when it's what minus 2 we do LL, right? When it's positive 2 we do RR, right?
But we have negative 2, so it doesn't work.
Huh?
Because it's negative 2 and it's plus 1, so it doesn't work for both.
What do you mean?
LR.
Oh, do we go down a little bit more?
Yeah, down. I think we use LR because we have minus 2
Mm-hmm.
and the balance is 1.
So we have to do LR, right? Because A has minus 2, like this, right?
26.4.
Let's see if it's LR or RL. Maybe RL though. So A, let's see what's LR first. So when A has minus 2, and a left shall be with plus 1, like in our scenario actually RL, right? Because we have plus 2 and minus 1.
No, we have minus
Right.
2
For 8 and 6.
Oh, for 8 and 6.
Yeah.
Minus 2 and plus 1, right? So minus 2 and plus 1, okay. So minus 2 and plus 1, we do LR, right? LR means what?
To the left and then to the right.
Which one to the left?
I think we should move 7 to the top to 6.
Assume B's right side is C, right? This type of imbalance can be fixed by performing a double rotation. First, a single left rotate at B. So we move this guy C up, B down. And then it's like this. So for that image, right? Let me show that LR first. So LR, we said what? A, B, C, right? A, B, C. So we have to rotate this guy L first by rotate this way. So you have A, but C, and B. That's L, right? And now you do R, which is this guy's gonna go up, right? So this is L, this is R, to the right. So it's gonna go up to C, B, A. Make sense? Now let's notice, let's observe like the child or the subtrees. So when we rotate, so T2, I want you to observe where T2 is going to go. T2 is going to go to the right of B, see that? And T3 is going to go to the left of A. That makes sense, right? Correct? Because T2 always less than but greater than B, right? Like for example, if I have X here, where would it go? It's going to go to here, right? It's going to go to here, correct? Yeah?
Yeah.
And if I have,
I got it. I think I got it.
got it?
I do.
Yeah, if I have Y here,
So,
where would Y go? Y is going to go here and go to the left of A, right? Correct? Make sense? Okay, so that's called LR, right? Are we going to do LR here?
Yes.
yes.
And again, this is minus 2 and plus 1, right? So minus 2 plus 1, this guy, right? So we have to do this. So meaning that we do left on 6, right?
Yes.
So the key we left on this guy, so we gonna get.
4, 3.
Do we need this?
No.
No. Okay, let me erase this. So we would get 4, 3, 8. Now we do rotate, right? Rotate this guy, right? Left. Then we get 7, 6, right?
Then we rotate to the right now, right?
Yeah, that's L, and then we have to do R, right?
In terms of 8.
So we have to do R. Now we're gonna get 4, 3, 7, 6, 8. Okay, let's check the balance, right? 0, 0. What's this 0, right? 1, right? That's 1, right?
No, it's 1.
Yeah, yeah.
2, 1.
Yeah, 1. Okay.
And also 0.
Alright, let's check on the animation. So, what's the number?
7.
7. Is it correct?
Yeah.
right? Because rotate for you already in that, right? But that's how we rotate, right? LR. So now we do 5. Where would 5 go? Greater than 4. It's going to be here, right? Alright, so check the factor again. So that's 0, 1, 2, 3. 3 minus 1 plus 2, right? 1, 2, 1 minus 2 minus 1. 0 minus 1, and this is 0. So we have to do rotation around here, right? What type of rotation? Plus 2. Plus 2 is it LL or R?
Yeah, it's LR.
Huh?
Oh no, it's RL. It's RL.
It's RL. I think we should check the book.
Alright, go back. So we said RL A has a balance factor of plus 2. And the right child B with a balance factor of, that's it, right? RL, right? Minus 1. So let's look at example RL plus 2 minus 1, exactly like that one, right?
It's supposed to be a 1, not a negative.
0 minus 1, right? Because right minus, I mean, if you look at the YouTube, it's 1, but if you follow the book, it's going to be right minus left.
Let's follow
Well, so we're going to go with the book. Yeah, we go with the book. Now we do what? LR, right? No, RL, right? RL. So RL said, okay, let's look at the definition first. RL said you're going to have to rotate what? Type of imbalance can be fixed by performing a double rotation. First, a single right rotation at B, and then single left rotation A. So single right rotation at B, meaning, let me draw it down, right? A, where would you go? A, B, C. Okay. B, C, right? Plus 2 minus 1, right? So single right rotation at B, right? Meaning we're going to get what? A, single right, C, and B, correct? And then we do left RL, right? Left back, then we're going to get C, A, and B, which is correct, right? Now, we have to notice something like, what happened to if we have X here? X always go there, right? How about this guy? I think this is a key. What's that one?
I think that would be the left children of B.
So we have X and Y, right? So left children of B, right? So X should go, like X gonna go here, right? And X will go here, right?
No. X
Y, I
gonna
think it's
run
Y.
A.
I think X would be the right children of A.
Right of A. And then Y.
Right,
is
X will be right children of A.
left of A.
So X gonna be here, right? And Y is gonna be here, right? Correct?
Yeah.
Now we're gonna apply it here, right? So which one again? Rotate at what number? 7 or 4? 7. 7, right? So 7 we do right rotation, we get 6 up, right? So we get 4, 3, 6, 5, and then what? 7, 8, right? And then we have to do again. We do right, then we do left. We do left at 6, correct?
Yeah.
We bring 6 up, correct? Yeah. Now 5 should go to the children as 4, like we said, correct?
Yeah.
So we gonna have 6, and then what? 4. But 5 belongs to this guy now, right? And then 3, and then 7, and then 8, and 9 should be balanced, right? Okay. So what are we inserting? 5, right? Let's check animation. That's correct, right? I think that's the one that we were confusing right
Yeah.
now.
That makes sense. A lot more sense.
Alright, so now 2. 2 will go where? All the way down there, right? So this is going to be 2, right? Is it balanced? Let's check. 0,
-1. 0. Oh, no, no.
because -1, right?
-1, yeah.
And this is 0, this is 0, this is +1. Now this is what? 1 minus 1, right? Then that's still balanced, right? Now insert 1. Go down here. Should be balanced.
Oh, no. 1 goes.
Oh yeah, you're right.
It goes all the way there. So it's not balanced again. You have to balance it again.
So 1 go down here. Now this whole thing is changed in that case.
Yes.
So 0 minus 1
-2.
minus 2
-3. Or,
No.
This -2. This -2.
because it's this, right? Minus 2, and then how many ever? 1, 2, 3, 4. So minus 4 minus 4 plus 2, right? Correct?
It's -2, yeah.
Minus 2. Alright, so how are we going to rotate this? Let me give you this anymore. So we seen all the LL, RR, LR, and RL, so let's revise a little bit. What LL is what when it's +2, is that right? RR when it's what? -2. And then LR when what? Is it +2 or
LL is -2, I think.
-2? LR is -2, right? And +1, right? That's +2, +1, something like that, right?
LL is -2. And RR is +2. Just switch LL and RR.
-2, yeah, +2. So how would you rotate the last one? -2 minus 1. -2 minus 1. +2 +2 +1. This actually makes sense, right? L is -2. R is +2, right? If you look at that, like plus. That's why L is -2 plus 1 LR, right?
So right is always will be plus.
Or yeah, left is negative, right is positive. If you remember that way, right? And then when the side is the same, then you just do L. Side same R. Side opposite is LR. Side positive is RL, right? Positive comes first. So now this image. So let's look at, we have a
-2 at the top.
-2, -1, right? which is we have to do LL right there. Correct? So 6, 4, 7, 8. This way. So what else?
5,
5 here, right?
3. Here we change.
3, 2, 1. Here's where we change because minus 2, minus 1, LL, right? LL mean we rotate 2.
Right, 2.
Yeah, we have 2 here, right? And 3 here, and then 1 there. Correct? So this is now we check a factor. 0, 0, 0. Minus 1, right?
5 is
0 plus 1 minus 1, right?
1 is
Minus 3 minus 3 plus 2, right? So that should be the answer. So we insert what? 2 first. Okay. It's easy, that one. And then 1. It's the same. That's it. So now it's always balance. So balance give you log A when you search.
so
Let's see if you search for 3. 1, 2, 3 times. That's the max, right? Like, what's the size of this? 1, 2, 3, 4, 5, 6, 7, 8. So log 8 is log this 2, right?
yeah, 3.
Max. Max 3. See that? Instead, obviously you do linear, it's going to be 8. Can you believe that people can think about this? We can't. I can't. Well, someone happened to, what his name? ABL, right? Happened to, Russian scientists just happened to sit and think, hey, we can do this to make it balance. I don't know how they do that, huh?
We had it implemented.
We just try to understand text over. That's why we don't get admitted. He's laughing. It's true, right? Because they only want PhD who can think like that. We can understand, but we cannot think to that. Alright, so I guess we pretty much finished BST and AVL at the same time, you know that? Maybe you noticed that. Those are the main concept for insert. For insert, right? Now when we talk about remove, you have to remove, then you have to make sure it's balanced again for AVL, right? And also insert has to be BST also. Now let's go back to go through BST a little bit. You see that binary search tree pretty much is very important. It's applied in heap, right? Now it's applied in AVL, right? Alright, so we were talking about insert. Binary search tree. Yeah, I have to click on this one. That one we will not be able to click. Alright. So now we understand the algorithm, right? So the rest of the chapter start to talk about how you're going to implement it. See that? You create a class node that has left and right. Instead of before linked list we have only 1 pointer, now 2 pointers, right? And now, yeah, with the elements, right? When you do constructor, you just initialize the element. This is just whenever you do is if an integer, you just parameterize it to the type, right? Give the type to the generates type. Alright, so this is just root dot left equals to the new one that's smaller, right? And root dot right equals to the new one that's bigger. This is just a binary search. That's binary tree, right? When you search, you just need to think about how. So the challenge is how to implementing it actually, right? So how you're going to provide elements. You have to go to search. You have to compare, right? So while is current pretty much just we pointer to the root. Let's say I'm looking for what 3. So I give my current pointing to number 6, right? So I initialize to 6. So this is my current. All right. So now I start to iterate by comparing current.get element, right? Dot. What method we want to use? Compare to 3. Then you get the negative. Now you see that negative has to shift to the left. Then you move your current to the next one. Right, current to the next one. So you see that current dot left because less than, right? So you move the current to the next one. So I move my current from that line. That makes sense? Now we do the same. What's the method we use? Dot compare to. We give negative if it's less than, positive is greater than, 0 if it equals, right? So it's going to give you a negative again. It's going to move your current, right? You use the loop and you if inside the loop to compare. Now 3 happen to be greater, so you move the current to the right and you compare, which at that iteration you pretty much just found that return true because match. That's it. That's how you implement search. Okay? Insert, we talk about the algorithms. This is just BST. This is not the balanced yet, right? Which balance we have to do the ABL technique to find a factor to make sure it's always balanced. But the technique to search should be the same after balance, right? So insert, you just need to check if a tree is empty. If a tree is empty, then you pretty much just write a code to create a node right there. Else pretty much just parent equals to current equals to root. Just start from the beginning again to find location to insert and then iterate to it as long as not equals to null. Equals to null, that means pretty much get to the leaf, right? Because child of the leaf is null. So do the same, do compare and just move left and move right until you find location.
I have a question about search method. So if we say one object is less than other object, so we're using comparative?
Compare to, yeah.
Okay, so
Oh, this one is not using object. They use the integer. That's why it's just less than, greater than, right? Why you do the element dot compare to for the object, right? So now when we do the insert, right? So it's going to keep searching. You can see that the reason why we have to have another pointer because when you insert, you need to know who's the parent. Then you know that you keep tracking on your parent, right? And you keep moving your current to the left of that or the right of that. Like this one, I assume that duplicate will not allow, so that's why. Now, technically, when you keep doing that, it's going to get to the point that it's null, right? Correct? Actually, that's an insert already. Because you, let's say for example, I want to insert zero. Okay, I want to insert 0. So tree is not empty. Do else, right? Parent equals to current equals to root, right? So we have 2 pointers, right? So P and what? Current, right? This is a root, right? I want to insert 0. 0 is less than 6, so keep moving. E less than, right? Parent equals to current. Current equals to current dot left. Parent stay there, right? Current, right? And now you iterate it again, right? Because current not equal to null yet. You have to keep moving until you get to null, then you find a location. So you move parent and you move C. Correct? That's the next round, right? And the next round is the same. You move parent and then you move C. Yes? Because it's not null yet. Now, current equals to current that get left, which is null, right? So this is pointing to null, and this is your current, and this is pointing to parent. Right? Return. So pretty much now we exit this loop, right? Loop of that. Then you have to write a code around here. Let's say to insert. Let's see if they have the complete code. Yeah, create the new node and attach it to the parent. So technically you just say what node equals to new node, right, at that point. And then parent dot set either left or right if it's better, right, to the new node. So this one is not implementing, it's commented for you. After exit, you have to do that. Right here. Create a new node attached to parent. I think we can stop at this point because our time has come to the end, and we come back and finish the other two.